Okay, everybody, welcome again to the lecture Visual Navigation for Flying Robots. I hope that more people will come in during the lecture. So today we will talk about control architectures and controllers in general. So to give you the big overview picture on the architecture that you usually have on a robot, can look like this. For example, you have the robot, which is composed of several modules, you could say, and the world, or the physical world in which the robot is. And of course, the robot observes the world with its sensors, and that includes things like its position, potentially with GPS, its velocity with accelerometers, or odometry sensors, and acceleration. And on the other hand, the robot can modify its position in the world by applying forces and torques via its motors or actuators, and these will change its position in the world and so on. And then the interesting part, so to speak, for us is this upper part here, where we have to interpret the sensor values and generate suitable motion commands for the actuators. And usually you have a layered approach, and we will discuss these things in more detail today, but also in the coming weeks. For example, you might have one control loop that is responsible for the motor speed control, so it has to measure the speed of the individual motors and adjust the voltages accordingly. On the next level above that, you have an attitude estimation that estimates the orientation of the quadrocopter, and then determines or computes suitable motor speed values. But you can't directly tell a motor to achieve a certain motor speed, but you have to do that indirectly via adjusting the voltages and so on, and or the motor phases. And this is why you need this such a layered approach. And then on top of that, you can have a localization module that tells you your position in 3D space. And potentially have a position controller that moves your quadrocopter to a waypoint, and so on. And then also this waypoint, of course, is nothing that you don't have. It's not only that you have a single waypoint, but usually you want to follow a trajectory or have even a more complicated behavior that builds on top of it. Good. And so today we will mostly focus on these lower parts here. In particular, we will start with looking at the kinematics and dynamics equations that some of you might already be familiar with. So the kinematics describe the motion of objects in 3D space, and dynamics refers to the problem how forces and torques change, in particular the acceleration, but then indirectly also the position and velocity.
Sorry,
that's the rotation speed. So this says rotations per minute, I think. Yeah, could also say rotation. Yeah, just motor speed estimation. Good. So today we will in particular look at how motors work, because that's the essential actuator on a quadrocopter. And then, as I said, we'll look at motor controllers, because we need to know how we can actually make them turn faster or slower. Then we will look at the kinematics and dynamics, and at linear control, and actually a bit more on more advanced control. But yeah, you will see that. Good. I guess most of you have already seen a DC motor, or who of you has built such a motor in school? Two, only two. Okay, interesting. So this is probably the most simple motor that you can build. It consists usually of a permanent magnet. So you have a magnet on the outside and an electromagnet on the inside. And by applying a current to it, this magnet will also get will induce a magnetic field, and this can turn this coil here. And if you just apply a constant current, then it will move once accordingly. So if this, for example, applies here a north, so this is the magnetic field, north pointing upwards, then it will probably turn here to the right, because north and south are attracted. And of course, for a motor, you want this thing to turn continuously. So the idea is that you have a small, what's it called? Connection, electrical connection, and whenever this coil turns to the right, it will change the sign of the voltage, or it will reverse the sign of the voltage, and that will reverse the magnetic field, and that means that north then suddenly south is suddenly here and north here, and this will induce a force on the coil, and then it will move over to this side again, and then when it reaches this side, the switch will again switch the voltage back, making the north pole here, south pole here, and then it will rotate back. A DC motor by itself doesn't have a preferred direction, so in principle, depending on in which position you switch it on, it will either turn to the right or to the left. Right, because imagine, so when it once starts turning, it will of course continue, because then there is a certain preference direction. But it could happen that if you switch it on in a different position, or at least that's what I think. Yes, yeah. Imagine you start. Oh no, actually that's not true. That's not true. It will always turn in the right direction. Sorry, forget about that. DC motors always have to turn in the right direction, because this switch in the middle will make sure that it will always move. When it's down here, it will move here and in the other direction. Good. In any case, it's very easy to build such a motor, and at least I did it in school, and I thought that more people might have done that. You just need a wire that you have to wire around the coil, and either a permanent magnet, or you can again use an electric magnet with a stationary field. And usually then this is how such a motor looks like when you buy it. The disadvantage of this motor is that it needs these switches, and these switches are also called the brushes, because it has to conduct the electricity somehow. And this is usually something that wears off after a while, and especially for motors that are turning fast, this wear can become a problem. So a different approach to motors are so-called brushless motors, or AC motors, and this is what's usually used in quadrocopters. So here the whole idea is to reverse the principle. You have a permanent magnet on the axis, so this is the axis of the motor, and it has several permanent magnets around, and you have several coils here, and then the coils induce a magnetic field that will gradually move the axis. And the problem again is that if you apply a static current to this, then the motor will only move once into its desired position. So to make it rotate, you have to modulate this electric field around here, that it will start to rotate the motor. And this means that you usually need some electronics part, like this here, a motor controller, that switches these currents accordingly. So also in the quadrocopters, you can have a look at it tomorrow or next week. You will find that the motor by itself will look somewhat like this. So you have the coils and the magnets around it, and then a connection to a motor controller that will actually produce the currents. There are different winding styles of how to connect the wires with each other. I don't want to go too much into the details, but if you buy motors, or if you buy your own quadrocopter, you have to, this is an interesting property to look at. It's, yeah, I mean, there are more characteristics of motors, like for example, how quickly it reacts to how much voltage it needs at which speed, and so on. The main problem is, or one problem of brushless motors is that we need this motor controller, and the motor controller has to apply the right field to it to make it rotate. And if this motor controller wouldn't have any sensor, then it would induce a certain field, but you could never be sure that actually the motor is already rotating so fast as it should. So it could happen that the motor controller says, yeah, rotate at 5,000 hertz or 5,000 rotations per second or per minute, and then it might not do anything because it's not at that speed. So the motor controller has to make sure that it slowly starts and achieves its final speed. And to do that, there are different techniques to sense its position. More expensive motors have Hall sensors that are located inside of the motor to see, more or less to read out where the magnets are or where the coil is at the moment. Cheaper motors directly do measure how much voltage you have on the coils. The idea behind this EMF method is that an electromagnet, of course, not only produces a magnetic field, but it also reacts to a magnetic field. So when you have a magnet next to it, it will induce a voltage on the coil, and then you can read out this voltage again to estimate its position. But it's more noisy to do it in this way. By using a Hall sensor, you usually only get a binary signal then. So you know only very roughly the rotation of the motor, but still it's enough to estimate its speed from it. But the important thing is that using brushless motors, you always know the rotation speed because you can read it out. And it's important for the motor controller to know that it can slowly accelerate the motor to its desired velocity. So as I said, there is usually a motor controller, and some motor controllers are really simple, but in most cases, and also in the quadrocopters, these motor controllers really have an own microcontroller. So it's a real small computer or processor. And this microcontroller then estimates this rotation and generates a digital signal first that encodes the desired rotation speed. And then there is a motor driver or a signal generator that turns this digital PWM signal into motor phases. So in the easiest case, a motor only has 3 coils, and you have this a permanent magnet on the inside. And so it's quite similar to this DC motor. You switch on a certain voltage, it will turn, and then you move around this electric field or the magnetic field induced by the electromagnets to make the coil turn. And then these phases can look like this. This is a very simple pattern where you just have either full voltage or a linearly decreasing voltage. This is easier to build, but not super efficient, of course. So the motor is saturated, or the electromagnets are saturated, and this is not optimally efficient. So better microcontrollers produce more a sine shape signal. And then it looks like this, and that increases the efficiency. So the signal that's used there is actually quite common. So I thought that I'll show you a plot of how this looks like. This PWM signal means pulse width modulation, and it can be used, or it's actually used for a lot of things in electronics. The idea is that you. It's a digital signal, so it only has 0 or 1. It's a binary signal, and when it's 0, then it means 0%. When it's completely 1, it means 100%. And by having it only switched on for a short time, means then accordingly only a percentage of the signal. So with such a PWM signal, you can encode an analog value between 0 and 100%. More or less. And this is for example, used by analog remote controls. So when you have a microcopter or a quadrocopter that has an analog remote control, then usually it sends out a signal like this. So for every joystick or every axis that you have, the remote control will generate such a signal, and that will be transmitted to the quadrocopter. And then the quadrocopter has again an converter or an inverter to create an analog signal back again from this. Which part especially?
Generally, why do you control the speed of quadrocopters?
Of the motors? Yeah, I mean, I come to that in a second. We need to control the speed because we have to keep the balance of the quadrocopter. And we do that by adjusting the speeds of the motors because, yeah, but I'll talk about this in more detail. Good. Another important problem, and you might have seen this abbreviation here, the I2C Protocol, is also used frequently for motor controllers, but also for other things. Usually in a PC, the CPU, the temperature is read out via such a protocol. And also if you have Arduino microcontrollers, then they typically have such a port because it's very simple, and you have lots of extension sensors that you can attach to it. Is this a question? No. Okay. So it's a bit more complicated than the PWM protocol, but essentially it's a serial connection. So you have two wires. One of them gives you the clock signal, and the other one carries the data. And it's one huge bus, and everything is connected to the same bus. And then a master on the bus transmits messages and it addresses a certain piece of hardware by specifying its address, and then transmitting some data between them. It's relatively slow by our in comparison to other things, but it's really easy to implement and used by lots of platforms, in particular by the Microcopter platform. And I think I mentioned the Microcopter project before, but this is one of the large open hardware or open source projects on the internet. So if you see people who build their own quadrocopter, it's very likely that they use the Microcopter project for this. So this is part of the electronics of a microcopter. So in the middle, you see the so-called flight control board that does the attitude estimation and the calculation of the motor speeds. And then it will transmit the individual motor speeds to each of the 4 motor controllers. And as I said, each of these motor controllers has its own microcontroller again to generate this PWM signal, and an inverter to generate the analog current that is then fed into the motor. So here you see 3 wires, and these 3 wires go into the brushless motor then. Yeah, exactly. So this is how it looks like. And on the Ardrone, and that might be more interesting for you. So when you have the Ardrone next time in your hand, then you can have a closer look at the rotors. So this is one of the propellers, and you see there is a small gear here, and here is the motor. And then around it, you have some electronics, and this electronics part is actually the motor controller. The interesting thing is that at least via the smartphone app, you can also have a look at the motor controllers. So it gives you some feedback on the firmware that is used. You can upgrade the firmware on them. But you can also read out, and I think this is also even possible from Linux, it's also possible to read out the rotation speeds of each motor. I think it's not in the default driver, but there are patches for it to read this out. And I mean, usually you're not interested in this because you just assume that the motor will achieve its desired speed. But in principle, this information is there, and everything today is controlled by microcontrollers. Good. So far, this was this lower part here where we just looked at the estimation of the rotation speed, and then the motor controller that achieves this speed. But of course, as I said, the question is, why do we need that? And this brings us to the kinematics and dynamics. I guess for those of you who had physics lectures or maybe have some knowledge in mechanical engineering, then you already know, but otherwise I'll briefly explain you all the concepts that we require here. So the kinematics by itself describes only the motion of rigid bodies without any forces. So this means in particular that you have a rigid body, for example, that has a certain position in 3D space, potentially has a certain velocity, and maybe is accelerated in some direction. And then the question is, how does where are we in the next second, or how does do all of these values change? And dynamics is related to the question how do you actually, I mean, where does this acceleration come from? And acceleration is usually induced by the motors, for example, by the propellers that accelerate the air, that induce forces and torques on these rigid bodies. And in particular, a force induces a linear acceleration on a body, and a torque induces an angular acceleration. But I'll show you more examples of what this means. So to get started, what types of forces do you know? What forces can or are usually applied to rigid bodies to make them move?
Gravity.
Yes, gravity, most important force probably. But we've also seen another one with the motors. So what made the motor move? Exactly, magnetic field. Yeah, there's also the electric field and things like that. And yeah, wait, we'll just look at first at the kinematics. Good. As I said, we are looking at position, speed, and acceleration. And for the moment, we just do that in 1D to make it simpler. And assume that we have an action that specifies an acceleration of the object. Then we can build up or specify a linear process model. You've seen that from your, I hope you remember this from last week. So a linear model means that our current state in the current time step depends on the previous time step via a so-called system matrix. That is just a matrix that describes how the previous state transforms into the current state. And then there is a control that we can apply, and in this case our control influences the acceleration. Yeah, so let's have a look at this matrix. I guess you're already familiar with it, but in principle it means that so we have here position, speed, and acceleration, and the position just stays the position. Here is a 1, right? And then the speed gets integrated onto this position depending on the time interval that we are looking at. So the new position, maybe I'll write this here, the new position at time t is the old position minus plus the speed at this instant times the time delta, right? Everybody sees that. And the same applies, of course, to the velocity. So the velocity stays the same plus the change that is induced from the acceleration, and the acceleration just stays the same if we don't change anything. Good. So this is the process model that's underlying the Kalman filter, and that you partially have to implement in the, will have to implement in the second exercise sheet. Good. So for 3D, so this was now for 1D. How many states do you think we need for 3D? 6. So 6 or 9? 9, yes, because you have the same thing again for the y-axis and then for the z-axis. Good. Okay, then the question, of course, is where does this acceleration come from? And I mean, when you describe only a system like a Kalman filter, then usually you already have this. But in the real world, the acceleration, of course, comes from forces, like the magnetic field force or the gravitational force and so on. And the dependency between forces and acceleration is the following. The accelerate or mass times the acceleration equals the sum of all forces. So consider, for example, you have so first of all, forces add up. So a force is a vector, and you can add it up, which means that if you kick a ball, then you apply a certain force according to this blue arrow, for example, and you could split up this force into two components, one along the x-axis and one along the y-axis. But then this would correspond to the same force. And the acceleration, so this force corresponds to the product of the mass of the object and its acceleration. So this means that if you apply a certain force to something, then the acceleration will be smaller when the mass is larger, which is, of course, intuitive. It's more difficult to accelerate an object that is heavier. Good. There is a similar equation for the torque. So the torque is rotational force, you could say. So if you consider a tool like this and you push it here, push it downwards, then you induce a torque here on this axis, and that makes the screw spin, or potentially if there is a larger object attached to it, makes the object spin. And the relation again is more or less similar to the force. So you can sum up the torques, which are vectors. And there's an inertial matrix, J, which corresponds more or less to the mass for the force. So a heavy object will be more difficult to accelerate. And then this alpha here corresponds to the angular acceleration. So to speak, this is the 3 degrees of freedom of the rotation. Good. We've already named a few forces. Of course, there's gravity, and gravity, or the force that is applied to a rigid body, depends on its mass and the constant of gravity on Earth, which is 9.8 meters per square second. There are also friction forces for a quadrocopter in particular, or for a motor. There is static friction, viscous friction, and then probably most important for us, the air drag. That's also a form of viscous friction. This is where this CW value comes from. I guess you might have heard this term. So it describes how easy an object can move through the air. And the lower the CW value is, the less resistance you have when you move, when you drive as a car, and it has a low CW value, then the less gasoline it will use. The air drag linearly depends on the speed, obviously, of your object, on the fluidity of the medium, of the air, for example. But if you have an underwater robot, then this row here can be completely different. And it depends on the surface of your object. And of course, this CW value. And the better shaped your object is, the lower this CW value will be. For example, on the Ardrone, you might have seen, or you definitely have seen, the indoor hull. That's the huge styrofoam cover, but it also has an outdoor hull that's much smaller, and by that they decrease this the area of the object, and that makes the quadrocopter, on one hand side, it can fly faster, but it's less influenced by wind. Which is especially outdoors a problem. If you have a wind speed of 1 or 2 meters per second, then it will of course be pushed away. And if you have a smaller surface, then it will be less pushed away. There are also springs, of course. The spring force is defined by a spring constant and the distance of the spring from its equilibrium point. And as we've seen, magnetic forces and so on. Let's briefly look at one simple example, the so-called spring damper system. That is, in principle, what you have in a car when you're driving over bumps in the road. It's a combination of a spring and a damper. And this means that the overall force that is applied, so you have a rigid body here with a certain mass, and it's attached via a spring to the rigid world, the world. And the total force that's then applied to this mass consists of the damping force and the spring force. And then as we've seen before, the acceleration of the object times its mass equals the force. So in this case, we just have the force from this the damping and the force from the spring. And this means that we get this partial derivative equation. And in such an easy case, you can compute it or you can solve this equation in closed form, and then you get a shape like this. And this plot here shows a little bit the influence of the individual parameters here. So if you have very low damping and you start in a certain position, then of course your spring will oscillate up and down forever. If you add some damping, then this oscillation will quickly be removed, because the damping force is always counteracting your current speed. For torques, we have something similar. We have already seen we haven't seen that. So the torque is defined as the angular acceleration that is applied to an object, and it is related to a force. When you have, for example, an object like this is a rotation axis here, and you apply a certain force in this direction, then there will be, of course, some angular acceleration here in the middle, and the strength of this acceleration will depend on the magnitude of the force, but it will also depend on the radius. The larger your radius, the stronger the torque will be. As I said, the torques sum up, and there is this formula that relates the torque to the angular acceleration. And as I said, the actual angular acceleration also depends on the inertia of an object, which mostly relates to its mass. And then also for the torque, you can have friction. Similarly, a damping friction or a static friction, and so on. Good. And how has all of this to do with quadrocopters? As you know, you have 4 propellers on a quadrocopter, and all of them are running hopefully at the same speed, and this will accelerate air or move air from above the quadrocopter to below it, and this will produce a force that will move the quadrocopter upwards for each of these motors. And at the same time, of course, you have a gravitation force that will pull, again, the quadrocopter downwards. And as we've seen, all of these forces can be added up because they are vectors, and because of the construction, all of them are parallel. So the only thing that we have to worry about is the magnitude of the overall force, and that's just the sum of all these 4 forces. And when the thrust equals exactly the gravity, then the quadrocopter will stay exactly in the middle of the air. So this is what we try. And when we want to take off, then this thrust force has to be larger, of course, than the gravity. When you want to move down or accelerate downwards, then it has to be smaller. Now, when you are not exactly leveled, when you're not exactly horizontal, then this thrust force will not be or will not exactly cancel out the gravitation. And now we can use this principle that we can split up forces into individual components. So if this is our thrust, we can look at the force or the component of this that's parallel to the gravity and the one that's orthogonal to it. And now here you can see that for keeping the quadrocopter vertically in a certain position, this set force has to equal the gravity, and this force in x and y direction. So this actually has 2 components, of course, because we're in 3D. Will accelerate the quadrocopter forward or left sidewards.
May I ask a question?
Yes.
So you know the gravity force already? Is it static? The gravity force?
Yes, the gravity is, when you don't change the mass, the gravity is always static. Yeah. So yeah. exactly. I've shown you a diagram, I think, in the first lesson already on this. Of course, you want to change this, so you can accelerate or you can change your position by changing the attitude of the quadrocopter. And you can do that by putting a larger force on one of the motors than on the other side. So this is the side view. Imagine one of the motors is rotating faster than the other one. Then these forces here will not have the same size. And this means that we have an effective force applied here on our center of mass in the middle, and that will induce an angular acceleration. And this will make the quadrocopter turn. Depending on the inertial matrix, this turn will be faster or slower. So in particular, and that's interesting to know, the larger your quadrocopter is, the slower it will start to rotate. So if you have a very large quadrocopter, then its dynamic will be relatively slow, and then you have seconds time to see how it changes its attitude. While for a small quadrocopter, especially these palm-sized ones or even smaller ones, nano quadrocopters, they have really high dynamics because their inertia is so small, and they can really do flips within a fraction of a second. And that means, again, then that the control problem later on will be much more complicated. Good. So this is how we can turn to move forward or sideward, and but then the quadrocopter can also turn its heading direction, or can change its heading direction. And the way how this is accomplished is as follows. Each of the propellers induces a torque around its axis. So we've seen that two propellers always turn in one direction, and the other two turn in the opposite direction. And all of these, and this is built in this way, that the total torque that all of the four motors induce sums up to 0, which means no torque. But if you, for example, let these two motors rotate faster than these two motors, then the torque won't sum up to 0, and this will induce rotation around the central axis of the quadrocopter. And in this way, you can turn left and right. Good. Any questions so far on this part so far? Good. Okay. So return again to this overview. So this means, I mean, we've seen in the first part how you can control the motor speed, and now by using these insights about the kinematics and dynamics, we can compute motor speeds, or that will achieve a certain attitude, and this attitude again will lead to a certain acceleration in x and y direction, or change the yaw angle. And yeah, exactly. So there is one part here on the attitude estimation that we've discussed in principle last week, where we get in the measurements from the gyroscopes and the accelerometers, integrate them up in either in a Kalman filter or in a simpler framework, and that will spit out this rotation matrix that we need to compute these the forces in x and y direction, and which force the total force we need to put on the motors to keep the thrust force, the set force equal to the gravity. Good. The idea in principle is that we have several of these layers, as I explained before, and the reason why we can actually do this is because each of these layers runs at a different speed. Wait, I'll first show you this diagram. So this typical motor runs at maybe 5 to 10,000 rotations per minute. This is also where the sound comes from when you fly with the quadrocopter. And then on the next level, we have the Attitute control, and that usually runs at maybe 1 kilohertz. So it 1,000 times per second computes the motor speeds that we need to level the quadrocopter. Then on top of that, we have a position controller, which gives new attitudes to the Attitute controller every 100 milliseconds maybe, and then a trajectory controller or a task or a mission controller that maybe every 10 seconds specifies a new waypoint. And you see that there is always at least one order of magnitude between the frequencies of these individual layers, and this means that from the view of the position controller, for example, whatever attitude it specifies to the Attitute controller, it's immediately achieved, right? And also the Attitute controller says, for example, well, I need now a certain attitude. No, sorry, I need a certain motor speed. It will pass on this motor speed to the motor speed controller, and because this thing runs so quickly, it will immediately achieve this position. So the whole idea of cascaded control is that you have several layers, stacked layers of controllers, and the inner loops are so fast that it appears stationary to the outside controller. And on the other hand, the things that the outside loop asks from the inside loop happen so infrequently that it appears almost static to the inner loop. So this is the idea of cascaded control. Good. Now, how does this control problem how can we actually solve this control problems at all of these levels? I mean, so far I've only motivated you why we need all of this, but I didn't show you how to actually generate the control command at each level that we give to pass on to the next level. So the general problem is as follows, or the general problem of feedback control is as follows. We have a certain goal state that we want to achieve, for example, a motor speed or a position, and we have a certain measured state that normally doesn't match the desired state. So we need to compute based on these two measures a control signal that we can pass on to the next level, or at the lowest level directly to the motors, that will make the system achieve or reach its goal state. To give you an intuitive understanding of what this means is, imagine, for example, in the morning you're standing below under the shower and you desire a water temperature of 35 degrees, so you switch on the shower, water starts running, and then you start measuring it by standing below it, and then you realize that it's actually not at its desired temperature, but much lower. So and this is now the measurement that we get in, and then you can compare these two. In the simplest form, you just look at the difference between the two, and then you have to correct the temperature by changing the what's it called? The tap. Yeah, thanks. And then the water temperature will change after a few seconds, and then you measure again, and so on. And this is how you adjust it. So this is the general idea of feedback control. But now let's look at it in more detail. What does this mean? If we have a very simple controller, we could just say we look at the difference between the desired temperature and the measured temperature, and we have a certain controller gain, K. And this product here will directly give us the control that we have to apply. Right. So, for example, if we are if there is 5 degrees difference between, or we have measured 30 degrees, we want 35, then this would be 5 times a certain gain. Say a gain is 1, then we would apply a +5 to the temperature. Right, and then we have a plant here, or it's usually called a plant. This is the process. In this case, this is the shower, so to speak. The shower keeps its same temperature. It has a linear model plus the desired control, and the shower has some noise term, or could have some noise term, epsilon. We'll see in a second. And yeah, so this is the dynamics model of the plant, and then we make a measurement of that, potentially noisy again, and then we will use this measurement to compute the next control command.
Can I ask you a question?
Yes, of course.
What is the reason we are using gain for the
You'll see in a second why we need that. So imagine we set the gain to 1, and we have no noise and no delays. Then yes, yeah. So when you have a system like this, then you apply exactly one time step, and it will immediately jump to the desired temperature, right? Because you only have to give once a control of, in this case, the difference is 10, so you give a control of 10, and in the next time step already you have reached your target value, so everything is fine. Unfortunately, there is always some noise, both in the temperature that your apartment or that your shower gets from the heater, but also in the temperature that you measure. So and then if you do that, and then you have a gain of 1, then the temperature here will change strongly depending on the noise. So it could get very hot or very cold, so, which is one thing. You're not actually close to the optimal temperature that you want to achieve. And the other thing is that you can't really take your shower because you have to correct all the time, or you have to give control commands all the time. So one simple solution to this is to lower the gain. So if you have a smaller gain, then the correction in each time step will be much smaller, and this will make so your corrections will be smaller, and this also means that your conversions will be somewhat slower. But in the end, you see that the real temperature of the plant much better now achieves the desired value. So the red curve here is the real temperature, and the blue curve is the observation that we get. And the observation is noisy, but despite it's noisy, by having a low gain, you can approach the desired value very well. So it acts like a filter, actually. It's in principle always a bad idea to have high gains, because in the worst case, the following can happen. So imagine we are again at 25 degrees in the beginning, and then when you have a large gain of say 2.1. The control will be plus 20 degrees, and that will overshoot extremely. So after the first iteration, we will already be way beyond 35 degrees, and then we have to correct again, and then because the gain is larger than 1, it will again overshoot, and so on and so on. So you start to oscillate around the desired value, and that's of course not what you want. Even worse is when the sign is messed up. So does anybody have an idea what? So if you have a negative gain, for example, what that would mean? Well, let's have a look at this. And this can in the third exercise sheet, you will have to implement your own controller. And I'm showing this because it could happen. And then when you observe a behavior like this, then you know it might be the sign, or it might be too large. So for example, if you have a small negative gain, the correction will be applied in the wrong direction. So actually, while you should make it 5 degrees hotter, it will instead make it 5 degrees colder. And then it will already be 15 degrees too cold, and then next time you will, and so on and so on. So this means that the temperature will quickly drop. And then at some point, it stops dropping. So who knows what's happening here? At minus 270 something. Exactly. So this is the absolute 0 point. And this is called saturation. So it can happen that the system runs against saturation bounds. Even if you still give control. So you see the control is not 0 here, but it can't get any colder, which can happen. Good. And in practice, it's not only that that the system by itself is bounded or can get saturated, but also the controls can get saturated. For example, especially when you have a tap that you have to rotate, there is only a certain maximum speed that you can achieve, right? Making it, opening it or closing it. And this is then called control saturation. So, for example, if we can only change the valve, say by 0.5 degrees per second, then it could happen that it takes really long. Then we apply, or the controller says we need to apply a certain correction, but you can only apply part of it for a long time. So it is saturated for a while, and during this time the controller will you get this linear increase until at some point it converges on the right value. Good. Usually people from control theory draw this as controller diagrams as follows. You have the desired value here as the input. You have an observed measurement. You subtract both of them. This gives you an error value. And this error value, and only the error value, is fed into the controller. Then this controller computes a control command, U, that is then passed on to the plant. The plant is also subject to some noise, epsilon, and has an internal state, x, that in principle exists, but we can't read out directly. So we can only observe that via a sensor, which is again subject to noise, which might be different noise. This generates again our measurement. So I'm just showing this that you recognize when you maybe read a paper or you see a talk of somebody, that you know that this is exactly the same thing. This is how it's drawn or how it's visualized normally. And then these diagrams, of course, can get more complicated. This is the most simple case. Of course.
For the noises we are using those noise.
Yes.
How do we know the amount of the noise?
By experiments, by additional experiments. Either you look at the specification of a sensor, and then in the specification it will tell you this sensor is so and so accurate. But usually you have to validate that in an experiment. So with the Ardrone, for example, you could say the ultrasound sensor has a certain noise. So you could do several measurements at different heights and then see how much they change and yeah. But it's not tricky. It's a problem for itself to estimate the noise. Most of the time, people just guess, to be honest. But if you want to do it more elaborately or more sophisticated, then you would have to run real experiments and finding out how the shape of this noise is. Good. Next problem is delays, especially with the shower, and depending on the size of the pipe, there can be a considerable delay between when you give the control command and when actually the temperature changes, and that can lead to sensitive oscillations and overshoots, and then also to a destabilization in the worst case. So, for example, imagine that we have a time delay of, I think, 5 seconds here. So the control will start. Yeah, so the control starts after 5 seconds. It will immediately give the maximum possible positive control, and that will, say, immediately change the system. But until we actually can observe the temperature of the water, a certain time passes, and this means that we give too much, so that the temperature already here reaches its desired position, but we don't know about that. So it will, and we still give maximum control, and so the true temperature will go above the desired temperature, and after a while, we realize that we observe that it's now at its right position, so we remove the control, and so on. And this is, of course, not desired. One solution, again, could be to lower the gains. But why is this a bad idea?
Can I ask a question?
Yes, of course.
I don't quite understand the diagram, actually. So if how can we get the temperature the real temperature X if it's not through observation? I mean,
how can we know? I mean, usually you don't know the red line. I just draw the red line here for making it clearer. But in principle, the thing is you give a control command for a while, and you only observe, you only have access to your sensor. And the sensor measurement is delayed.
So the delay is because of two things. One is the observation of the sensor, and the other...
And the system by itself. Yeah. Sorry, I'll clarify this in a second. The delays can be, of course, at different points in time. You can have a delay here, within here, or here, anywhere. So in this case, the delay is in the observation, but you could also have, like in the shower example, sorry for confusing this, in the shower, the delay would be between the moment that you... Yeah, it depends where you consider, where you have the true X. I mean, if the X is directly in the valve, then the temperature would be immediately at its desired value. But until this water reaches then the top of the shower and you feel it, a certain time passes.
What is normally the delay for the quadrocopter?
It's around, so it depends on different things. Normally between 100 milliseconds maybe or 200 milliseconds in this order of magnitude.
Yeah, I mean, because of the measurement, because of the sensor, or is it because of the real model? Because if it's
both. Unfortunately, both. In the real thing, you always have all kinds of noise and all kinds of delays, and even not even constant delays, which makes it even more complicated. But I will show you more details on the quadrocopter in a second. So why is it a bad idea to lower the gains in general, or why do we want high gains?
It is slow.
Exactly. It would work, but then maybe you have to spend 5 minutes under the shower until you have the right temperature. Good. And then this is what we already discussed. Of course, you can have delays everywhere. And there might be some delay in the water pipe. There might be some delay in your skin. The question is, can you actually distinguish where the delays come from? You know, can the controller, or can you at this point here distinguish between these different delays? No, exactly. Because there is no way to tell, because you don't have access to the true state. You just observe something, and you don't know where these individual delays come from if you don't have additional sensors. Good. So one way to correct for this is the so-called Smith predictor. And this will allow us again to use higher gains, and higher gains means that it converges faster, which is usually what we want. But as I said, higher gains without compensation of the delays and so on may lead to oscillations and might destabilize your system. And the thing is why that you, for correcting for these delays, you need a really accurate model of your plant, and not always, and it's not always the case that you have such a model. But let's have a look at this, how this works. So again, we have our desired value, we have a measurement, and compute an error value that we feed into the controller. And now the controller outputs a certain control that we feed into our plant that suffers from this delay. At the same time, we feed the same control in a simulated model of our plant that doesn't have this delay. So this immediately spits out a predicted observation with no delay in principle. And then we can use this predicted value for our controller. Might be dangerous, of course, because this model might not be super accurate. So in principle, if you imagine this whole thing, without this, we could just have a simulated model, and when the model is super accurate, then this will be enough. This is like when you get into the shower after 2 weeks of training or a few days of training, you can almost blindly adjust it to the right temperature because you know exactly the plant model. And yeah, exactly. But of course, all models have some error, so it makes sense to compare our model with the real measurement. So what we do is we feed this delay-free prediction into a delay model that will just wait for a certain while, and then spit out again the same value. And then we can compare these two. And if the model is perfectly correct, then there will be zero difference. But of course, there will always be some difference. The plant model might over or underestimate the true value. So there might be some difference here. And then we feed back this difference and add it to our predicted value. And this will so this will effectively compensate the delay and also compensate for inaccuracies in the model.
What exactly does the delay model have as output?
So the delay model just takes in, we get a predicted temperature that we assume is right, and then the delay model, for example, says we assume that there is a 5-second delay. So it outputs here the delay from 5 seconds ago. So it's just like you can.
The predicted value for 5 seconds.
Exactly, the delayed predicted value. You would, in the easiest case, just have an array and then store all the values and then wait for a certain time. Good. So with this, you can again have high gains, even when you have a considerable amount of delay. And in the ideal case, without noise, this results in perfect compensation. But of course, this is unrealistic in practice for a number of reasons. One of them, of course, is noise, but another one is what? I mean, we've already discussed it somewhat, but what are other sources that might impair the performance with this model?
We cannot really have perfect prediction.
Yeah, exactly. The model will anyway be wrong, or will be a little bit wrong, and we don't know exactly the delay. And even if it could be that the delay is every time different, especially with wireless LAN connection. Sometimes it might be super fast, and then 5 seconds later it might be super slow. Good. So exactly, these 2 points are probably the most important ones. And now let's consider two cases. When we overestimate the time delay, so we think that the time delay is too large, then the following happens. You get again oscillations, because the Smith predictor thinks it's doing everything right, but then this delay model here spits out. In any way, there will be a mismatch then between the real observation and the predicted delayed observation, and this will lead to large errors that the controller will then compensate, especially when you have a large gain, and that might lead to compensations. On the other hand, if you underestimate the delay, it's usually better. It in any case depends on your system. But it's always so if you have a Smith predictor and you don't know exactly what your delay is, it's much safer, like with the gain, to have a lower value than a larger value. Because in this case, the Smith predictor won't, at least it won't do any harm. In the worst case, you just assume a 0 delay, and then you essentially have the same as before, like a controller with no, that does not assume delay. Yeah. Okay. Good. Good. So now with this, we can implement position control. Of course, we're not only so we have then in principle to deal with 3D waypoints and 3D poses. We have certain measurements from our localization module. This is the Kalman filter, for example, that spits out directly the position, speed, and acceleration, or sometimes only position and speed. The waypoint usually only consists of a goal location, but you could also have a desired velocity at this goal location or a desired acceleration. And this is especially important for high dynamics flight. I mean, when you're only trying to fly over waypoints, then it would be okay to stop at each waypoint. But to get a smooth behavior, you also need to specify velocities and accelerations at these waypoints. Yeah, and then the position controller will generate a control command U for the actuators, and the sensors will give observations that we can use in the Kalman filter to update our prediction. Good. Let's now see how this combines with the kinematics that we've seen before. Imagine for the moment just a single rigid body that is floating in 3D space with no gravity. How does such a system evolve over time? Well, consider that we have position of, so this is a 1D example again, we have position 0 and speed 0. Then obviously nothing changes. So these diagrams, briefly explain these diagrams because we have a whole series of them. We have 0 position, that's the red line. We have 0 velocity, that's the blue line. And we don't give any control command at the moment. So imagine we have a small velocity in the beginning, and we are in outer space, so there is no gravity. Then of course we will keep this velocity all the time, and so this is our small velocity here, the blue line, sorry, and because we have this velocity, our position will integrate this velocity in every time step, and so we will have a linear motion, right? Good. Now imagine we want to achieve a certain desired position. Say we want to move our body to x equals 1 by applying a certain force to this rigid body. And as we know, a certain force influences the acceleration depending on the mass. Good. And now we've already seen this simple control law for the shower example. So you have the desired position minus the observed or previous position times the gain, and this gives us our control. And this is called proportional control because the correction or the motion command is directly proportional to the error between the difference between the desired value and the previous value. And now, if we apply this to our floating body, then the following happens, and this is obviously not what we want. So we start at 0, we have a certain velocity, and now we can apply control commands. So the proportional controller realizes that there is a certain difference between our desired value 1 and our current position, so it will give a certain control, and that will increase the speed, or that will set a certain acceleration that will integrate to a certain speed, and this speed will influence again the position. So you see that our speed is increasing and our position is also moving towards 1. But then here at 1, actually we don't stop because our system still has a certain acceleration. Still has a certain speed. So we actually overshoot our goal again, and this means that, the system will immediately respond. In this case, we don't have any delays. It will produce a negative force, but because we still have a very high speed, the position will overshoot really by a lot, and up to 2 here in this example. And then here, the control commands will get very, very small, or will get negative, which means that the speed at some point also will get negative, which will make the rigid body return. And then again here happens the same thing. The speed is not 0, speed is negative, so we overshoot again. And in this way we get a strong oscillation. A good idea to resolve this is also to look at the difference between the desired goal speed at the desired speed that we want to achieve and our current speed. And this is then called proportional derivative control. So the idea is that this effect would not happen if the position would be 1 and our velocity would be 0. So this is actually what we want, right? So using this control law, we get this red curve here as our position, and you see it's nicely converging on our desired location, and you can also see that the speed converges to 0 as it should. And when we now look at the individual contributions of these two components, then you see that the proportional part is the red part. So the proportional part says we need to accelerate in this direction, and the blue part, right, yes. The blue part is this part here that controls the velocity, and this part tells us that we have to reduce the velocity, that we actually achieve 0. And both of them together lead to this dark green control, and you see that this dark green control is positive during the first few seconds and then quickly gets negative, because then the differential part here dominates, which will make our system to slow down. Good. If we set higher gains, there are now 2 coefficients that you can influence, but if you influence both of them or make both of them higher, then you can, or even one of them, you can again destabilize the system. In this case, it doesn't destabilize, but it just overshoots again. The advantage, in comparison to this, it took us maybe 10 seconds to reach the goal location. Here it takes even longer, so this is probably not a good idea. But you can sometimes find controller gains that will quickly bring your system to to the desired, to the steady state at the cost of overshooting. Good. If you have lower gains, then things take longer, obviously, but it might be more stable. Good. So now consider additionally, our body is not floating anymore in outer space, but now on Earth, and this means that next to the force that we apply, there will also be a gravitational force that will pull the body down, and this will mean that we don't reach our goal location of 1 meter, but it will actually drop very far. So if this is meters, right, then you see that the body drops roughly 60 meters before the proportional controller will give so large correction that it will pull up the object again. And this is of course not what you want, because before it falls down 60 meters, usually the quadrocopter hits the ground. The good news is that you can add additional terms to such a controller to compensate for this. For example, if we know that there is a certain gravity, then we can already include that in our formula to produce the right force. And I mean, for gravity it's very simple, but in principle any dynamic model can be included as well. And when we do that, we get again this nice behavior where the quadrocopter or the object achieves its desired location, and at this location has velocity of 0. Oh, sorry about this. Okay. So imagine that we have a systematic error. For example, you have an unbalanced quadrocopter, or you're flying in the wind, then it might happen at every time instant that a quadrocopter is actually pushed away to one side, right? It's a bit similar to the gravitational force, something that pulls your quadrocopter or that pulls your object away. And the question then is, does the robot ever reach its desired location? And the answer is no, when we don't consider it. Imagine now there is some force that pulls our quadrocopter up. So again, in the beginning, we accelerate towards 1, and then at some point we reduce our controls to 0 and slow down our object. But this additional external force will push or will blow our quadrocopter to a certain state above our desired value. And even if the proportional controller tells us to reduce it, there will be at some point an equilibrium between this external disturbation and our control, and it will not lead to the desired state. Is this clear so far? Okay. This can be resolved by using a so-called integral control part. So I mean, so far we had this proportional controller, the derivative controller, and now we're adding an integral control component that looks at the overall difference over time between our desired value and our current value. And then this term here will, I mean, ideally it should be 0 if there is no disturbance. But when there is a systematic disturbance, then this term here will compensate for that. So you see here, the quadrocopter is moving upwards. It's being pushed away by the wind. And now we have a certain deviation between our goal location and our current location. And this will make this integral larger than 0. And the longer we are above our desired value, the larger this integral will get over time. And and the more and more this integral part will pull back the quadrocopter. And this is in general, or this is in principle a dangerous thing, because or let me first start like this. For steady state systems, this is a good thing that you can do. And these are systems that can actually reach, or that actually reach their desired goal location. But if a system can't do that, and I'll show you a few examples. Yes?
Since I'm integrating from -infinity to now, even if I reach my desired position, I
Yes.
So also compensate for all past errors, even if they are corrected now. So.
Yeah. This leads to a small bias here, but hopefully at the end, this will the whole thing will converge on the right desired value. So but in principle, if you look at this curve, so you're right. So it's the distance. It's this area here, and this area have to compensate. So this will this part won't give 0 control output as long as this area and this area is not the same. True. Yeah, but this is exactly the thing. If you for a very long time can't reach your goal location, for example, you might get stuck. The quadrocopter might get stuck somewhere in a tree, and for a very long time it doesn't get here. Then this area will get larger and larger, and the control output from this integral part here will be really large, and that can again lead to the so-called wind-up effect. That I'll demonstrate here. So again, we want to move somewhere, but we can't get there, so we get stuck here, and this means that this integral part will grow larger and larger, but our system is saturated for some reason, and then when we want to fly back, because we realize, for example, that we need to that we can't get, so a higher level module in the architecture realizes that we need to abandon this waypoint and do something else. We specify a different waypoint again at 0, and then this integral part will actually keep us from giving this control, because the integral part still says there is so large systematic error that we have to correct that your system doesn't move at all, and this is of course not what you want. Good. The next concept is usually, so far we've only looked at 1D problems, which is called a single input, single output system. But of course, in reality, we live in 3D space, and potentially there are even more degrees of freedom. So there are multiple inputs and multiple outputs, which is then called a MIMO system. And while it is in principle possible to create controllers that take multiple inputs and control multiple variables at the same time, control is often decoupled, which means the following. So if you have, for example, 3 axes for a quadrocopter, also in your homework at some point, it's wise to just have 3 different controllers for each of the axes. Of course, the X and the Y axis are somewhat related because you make rotations, and so it makes a difference whether you, so there is some influence of them, but in most cases it's just sufficient to assume that they are actually separated, even if in the plant there is some influence between the individual variables. Good. Now, one problem that we haven't looked at all so far is how do you choose the coefficients of such a PID controller? As we said, if you make the gains too large, then overshooting, there will be some overshootings and oscillations. If you make them too small, then it might be stable, but it might take very long to converge. There are some heuristic methods to tune them. So one method, for example, so there are different procedures where you first select the p-value and then select the next value and so on. But in practice, very often they are tuned manually, and that requires some experience. And also in the third exercise sheet, you will have to fine-tune a little bit these parameters. Good. So now let's look again at the Ardrone and at this cascaded control. We have an inner loop on the Ardrone itself that does the attitude stabilization, and of course an even further inner loop that does the motor speed control, which happens directly next to the motor. But the attitude control, runs on the Ardrone. It roughly at a rate of 1 kilohertz, and and then it sends back the images to our external laptop or to your computer at maybe at 15 hertz, and then the outer loop will compute roll and pitch angles that are then achieved or executed by the inner loop. More specifically, this means or could mean the following: the inner loop controls the motor torques. The motor controllers get motor torques that are computed from the Attitute controller, and then the inner loop measures again the roll, pitch, and yaw, and the set velocity or the set position using its sensors. The outer control loop that runs off-board on the on the laptop gets again the odometry information and sorry, I'm a bit confused. Yeah, and then sends back images, and these images are being transformed then to positions in X, Y, and Z direction. And from that, the outer loop will generate a position control command that, so this outer loop here corresponds to position control, and then to get to a certain position, it will generate certain velocities for roll and pitch, and they're controlled via roll and pitch and so on. Good. And now there's one interesting note here. You might have seen that before. Ooh. Wait. There's something. I need to start it like this, I think. So the PID controller corresponds to this spring damper system that we've seen in the beginning, and this is also visible from here. It almost looks like, so this is Jakob. I think I've shown this video before with the Ardrone, and you can see as if there were some virtual springs that keep the quadrocopter in position, and this comes from this PID or PD control that Jakob here applied here. So whenever you see a behavior like this, then you probably know that it's a PID controller running under the hood. It can be any combination, actually. P stands for proportional, D stands for derivative, and I stands for integral. And PID is usually the term that people use to refer to this kind of architecture, because if you don't want the integral part, you just set the coefficient of the integral part to 0, and then you get a PD controller. But yeah, I mean, you have all combinations, and depending on your application, you just need P control, for example.
Can you get a picture of how it's related with the spring PD control?
Yeah, right. So in this case, it's just PD control. Yeah, you don't have an integral part here. True. So we've seen, so just to summarize this a little bit, we've seen P control is often enough, but it just does proportional control, so it might suffer from oscillations and systematic biases. The integral part can compensate for such a bias. The differential part can be used to reduce overshoot, to make sure that the speed at the go location is 0, and the PID control can do all of the above. And PID control is a how do you say mostly used method for control. Yeah.
I have a question.
Yep.
What is the for the integral part? What is the mechanical equivalent? And for
good question.
For the part we have the spring.
Yeah.
For the differential part we have the damper. And for the integral part.
I don't think that there is a mechanical equivalent for this. I'm not sure. Maybe somebody knows. I don't think there is. Good. Now maybe to close the lesson for the lecture for today. So there was a funny example that I've seen a few months ago at the Munich Nerd Night from Georg Eggers, and this is also where I got these slides from. So he's actually a comedian, and he's really funny. So he explained PID control with the example of going to a beer garden, and there are of course certain actions that you can take, and there are certain system dynamics. So when you come to the beer garden, you obviously want to order a beer with a desired value of 1 liter. right? That gives us here our goal. But of course, when you make a measurement, you already realize that, that you're not at your desired value. So you have to order a beer, and you do that by calling for the waiter. That will then hopefully, move your level of beer towards the desired value. However, you see already here one problem, which is the so-called quantization error or discretization error. That even if you order one beer, or even if you send a certain control command to the to the waiter, in this case, it does not mean that it's actually executed as it should be. So then, after a while, you start drinking. You, of course, have strong thirst, because it's your first beer. Which means that after a very short time already, you will hit again the 0 level. And then nothing happens for a while. So this means that so this is again saturated here, so-called dry run of your system. You have to call again for the waiter. You get the next beer, it suffers again from the same quantization error as before. But because you had this dry run here and you called the waiter several times, oh no, sorry, one thing, yeah, you drink a little bit and then you get a second beer, which actually leads to this overshoot here again. So now we are far beyond our desired value. Yeah, you have to overshoot. Then you start again to drink, and then something happens, which is due to a smoking break. So the system gets shortly delayed. Then you start again normal drinking, which is the so-called nominal thirst. And then this is something maybe specific to Munich. So-called Nockerl abräumen, which means that the last part of the beer is actually removed before you can finish it. Of course, when you realize that, you're getting in a really bad mood, and this because you're a bit angry and shouting at the waiter, you throw over the beer tray of the waiter, which will even lead to a negative value of your beer level. After a short while, you can at least move it back to 0. And then, unfortunately, the beer level here stays at 0 because you're being banned from the Beergarden. Good. So I should not notice, yeah, so I just thought that this was a funny example.
Just for clarification, I think a controller would actually, when you have this normal thirst, would it stop at the 1 liter and then just have it standing there?
Oh yeah, right. And this is where the model is wrong. Yeah. Good. Yeah. Exactly. Yeah. This is it. It does not perfectly fit, of course. Yeah. Yeah. I mean, so to speak, it's actually more that you want to. Yeah. No, you're right. It's yeah.
I mean, you wanna always have a beer next to you.
Yeah. In principle, you should start already here to order the next beer. Because also given the delays in the system, this you might again run into a dry run again. So yeah, right. That's a good point. PID control is the most widely used control technique, and we want you to implement that in the third exercise sheet. But there are, of course, much more control techniques that I didn't discuss here. So there is, for example, adaptive control. I'll just briefly discuss the fields that you have a rough idea what this means. Adaptive control means that you change the coefficients, or that you change your controller according to a meta observation from how good your control is. So, for example, if you see that you're controlling something very well, then you could increase the gains. If you see that there are oscillations happening, then you could decrease the gains and so on. Another domain is called robust control, where you not try to achieve the desired value as fast as possible, but that it even works if there is substantial noise on your signals and potentially changing noise. So for an airplane, for example, you maybe not want to have the very best control or the fastest convergence, but you want to make sure that even if one of your turbines is suffering a small problem, that you're still not starting to oscillate and so on. There is also a lot of optimal control theory, which tries to minimize a cost measure, and one of them is the so-called linear quadratic regulator. All of them assume that you have a good, or at least the linear quadratic regulator assumes that you have a good model of your system. And then there are some machine learning techniques like reinforcement learning and inverse reinforcement learning. I think given the time, I will skip everything except the videos, which are actually nice because people apply them, of course, to all kinds of problems. So, so this comes from ETH, where they learn to make flips, and then even if you have a good controller, it will of course not. I mean, no matter how good you fine-tune your controller gains, you can't immediately get gains that that will lead to a stable flip. So one thing that you can do is to have human learning in the loop, right? You adjust the gains until it does the flips correctly. Or you can have a machine learning technique, the so-called policy gradient methods that iteratively change the controller gains until you end up with the desired behavior. But this is definitely more advanced and not something that you can do in a day or so. The same problem also happens, of course, if you want to follow a trajectory. Then your quadrocopter normally will do anything but fly the desired trajectory. But in every iteration, you can adjust your controller parameters, and then after a few training runs, you see that it more and more converges onto the right one. And the challenge here, the scientific challenge, and this is actually really an ongoing research, is to use as few as possible iterations. So the first reinforcement learning methods used 1 million examples. So for example, reinforcement learning or Q-learning was applied successfully to solve the backgammon game in the mid-90s. But it took, I think, at least 1 million of games where the computer had to play against itself to get as good as a human. And you can do that with a computer game, but of course not with a quadrocopter, because every time it crashes, it's really bad. So the challenge is to make it from very few iterations. Another option actually is to learn from humans. Sometimes you have experts that already know how to fly something, or you have a first controller that does something. And then the question is, in inverse reinforcement learning, how can you use the demonstrations from the expert to fine-tune a controller? And the idea here is, again, that you have an expert that flies maybe a flip with a helicopter or a quadrocopter. And then you use, again, simulation to fine-tune your parameters, and then at the end you fine-tune them on the real thing. But this is just to stimulate you. So if you're looking at some point for a master thesis project, things like that are really interesting. Trajectories?
Helicopters, yes, trajectories.
I think this is a visualization of the not available. Visualization of the demonstrations. So every time a human pilot flies it, he will fly it somewhat differently. And I think this visualization just showed all of the training examples. Yeah, the red are the demos, and the green one is the learn trajectory. And it's of course complicated to extract the important parts from a demonstration. So you don't want to fly exactly the same trajectory, of course, in X, Y, and Z coordinates, but you want to distill the controller parameters that make your controller output control commands that then in turn lead to such a behavior. Good. So to summarize, we've looked today at brushless motors, which are the normal motor used on a quadrocopter. Looked at the motor controllers. We also looked at cascaded control and PID control. And I showed you a few videos of more advanced control techniques. Good. So this is it from my side. Thank you again. One last thing. Jakob told me that he will. So first of all, on Thursday is holiday, so there is no lab exercise. But he will. He's preparing the exercise sheet for next week, and he will have a first version of it online either today or tomorrow morning. So and the lab will be open tomorrow afternoon. And the first subtask will be to fly the quadrocopter by yourself and take a group picture of you and your group with the quadrocopter. And for those of you who already want to get started, can come tomorrow afternoon. But otherwise, the full exercise sheet will be online probably on Thursday or Friday. And then you can do it next week. Good. Any questions? Good. Okay, then see you next week.